Alright, so we're looking at number 11, and just so I don't have to scroll, remind me what the directions say.
Just find the domain of each function.
Okay, so we're not worried about continuity just yet, we're just finding the domain. So we have two issues in here out of the three potential ones, which is we can't square root a negative, and we can't log either 0 or negative. So we have both those issues to look out for. So x minus 7 has to be greater than or equal to 0. So that's one issue. And then also square root, let's change color. Square root of x minus 7, just it can't be 0 or negative. So I guess we could say strictly greater than 0. But we have to be careful there, because I'm not saying in this case, but in these log ones, we saw probably this one would be that way. Number 7 looks like. Anyway, we saw yesterday in the notes where there could be weird cases where you split your interval to make it make sure it's not negative, in other words, right? Yesterday we saw that it couldn't be between 0 and 4, because that was what made the inside the log, it made the fraction negative. Alright, so we've talked about concept. How do we figure out, this one's not too bad, but he's asking because the key had an error, I think. You said it, what did it say?
It just said x minus 7 has to be greater than 0. But would
it said this, you're saying?
Yeah, but wouldn't it have to be 7? Because you
yeah,
can't
why did I
root a
write
negative.
Here? Hold on. 7. There we go.
Okay.
Sometimes when I talk, I don't think when I'm writing. Sorry about that.
Okay.
Like, poor writer was gone golfing yesterday, and so I'll show you my note error that totally threw him off. Anyway, so yeah, if it said -7, you're saying the key said -7?
No, it just said 0.
Oh, 0. Yeah, because if we plug 0 in here, obviously that's going to be the square root of a negative. So that's not okay. And then in this case, like if we solve this, where is this positive strictly? It's basically the same because we can just square both sides. And so that follows the other, because of the square root kind of protects us from being negative. Let me say it that way. Right?
Right.
The only thing is that we also can't be 7. So this or equal to part has to change to strictly just greater, because we can't have that 0. So we when we combine both, it becomes that, but definitely not 0.
Okay.
Sorry about that.
That's okay.
Just to show you what I'm talking about. Look what I wrote. We know it's supposed to say even roots of negatives, but it just says evens of negatives. So that's confusing. Alright, any other problems to talk about on the homework?
Number 10 on the next.
On 113.
Yeah.
Can you do 14 on test prep?
Yeah, is it on this?
On 112, yeah.
Is it on this page?
It's on the next
Next page, okay. Works. Alright, not continuous means we're looking for what? That's kind of a big big question, excuse me. Well, is cosine continuous on that interval?
Yeah.
Yeah, it's fine. How about what happens when you have a negative exponent? Do you guys remember? Yeah, so let's be careful and like if I have this 1 over 2, well that's this case, so let's just start with the easier case. If I say 2 to the -3rd, that means take 2 to the 3rd and make it positive in the denominator. Then make the exponent positive but switch place, right? But if we had 1 over 2 to the -3, again we switch place with it and make it positive. So it does both things, right? So is this actually an issue? That's the question. We could rewrite this as 1 plus 1 over 2 to the x in the denominator. Sorry if that's too small. 1 plus 1 over 2 to the x. So is there an issue there? Will 2 to the x, well, first of all, the issue would be if that, just, I'm going to write it bigger so I can talk about it. Would first be if this is 0, that would cause an issue. But also if this whole denominator is 0 as well. So can 2 to the x ever be 0? Okay. Because what kind of function is it?
Inverse.
What did you say?
Inverse.
No.
Inverse exponential.
It's exponential. Not inverse exponential is log.
Oh.
Right? Okay. Can this denominator ever be negative? Because the other two pieces of the big denominator are positive, like positive 1, positive 1. Can 2 to the x ever be negative? So, and I'm asking that because that's the only way that we would add to 1 and make something 0, right? Is if this was negative. So that one's okay. It's also a good one to review. Everybody understand why? Alright, next one. This is a 6-degree polynomial with a positive lead coefficient. Do you guys remember that stuff? Like, it opens up. It could potentially cross the x-axis and give us some zeros though. But let's say all of those were 0. Is that negative 2 okay? Like 1 over negative 2, do we worry about that? So really we need to know if this ever if all this junk ever equals negative 2. So how do you figure that out? I mean positive 2, excuse me.
Too much math.
Like if we found the zeros, those would be okay. But not if some weird chance that added up to 2. Huh? Some chance that it does. I don't know if I agree with that. Do you guys remember what even polynomial graphs look like?
Yeah.
Or potentially look like? Well, remember, first of all, they have the same end behavior on each side. But remember, they can like do this kind of stuff, right? Or maybe it just happens to just kind of flatten out and come up like a parabola. But point is, like, if it has the potential to do that, it could hit 2 several times, right? Writer. He thinks it's unlikely. Or it could hit 0 if we want to think of it that way instead. So it definitely has the potential for the whole denominator to be 0. And then this last one, does it have any issues of continuity? Who cares, right? It's totally fine. So, did that help? Trevor, is that you who asked that one?
Yes.
Did that help?
Yes, because B was what I was really not understanding. Started with B. He walked through it.
Okay. Any others? Oh, you had one on the next section.
Here, I have a general question. So you said do test prep with 1.13 too? Well, you said do 10 through 14.
Yes.
And then you said also do test prep, but 13 and 14 are test prep.
Yeah, so you're
So, okay.
right.
Number 10 on 1.3 or 1.13.
Alright, just checking this one. Right, or listen up, this is what we were just now talking about over there. Alright. So remember we have to check the pieces. I'm going to abbreviate the notes from the other day, from yesterday. Check the pieces for domain issues. What could you add as a couple words to clarify the last thing we noted on this yesterday? Remember how we had that 7 that was an issue in the piece, but it actually wasn't in the bigger picture? Do you remember what I'm talking about? How could you say that right there? So check the pieces for domain issues. I have an idea of what I would say, but this is challenging you to think through. your own description. You guys know what I'm talking about? I think what I'm referencing is 112 yesterday, where we had to check pieces for domain issues and then also make sure those domain issues actually fell within the given interval. Remember that? And I know this isn't that, but I'm just reminding you domain and continuity stuff. Does everybody know what I'm getting lots of blank faces. I know I'm talking about a slightly different concept from what this asks, but do you know where I'm going with it? Okay? Like, if this was that kind of question, we couldn't have a -7 right there. Does that fall within our domain interval? Yes, it does, right? So, well, in this case it wouldn't, but anyway, I think I'm just making it worse, so never mind. Let's just stick to the problem at hand and we'll review that separately. Okay, for what value of c is f continuous at x equals 7? Yesterday you got pretty good at saying let's just set them equal, so the two pieces. But I do want to note that notation on these should really be a little bit tighter than what I showed you when we were running out of, oh, I guess we didn't run out of time. I should have just showed you this a little bit better. Can we plug in -7? Let's start there. To solve for c, can we plug in -7? No, because why? That makes it a 0 denominator and we're stuck, like we're not getting anywhere. Well, but there's no, we're not solving for x, we want to know c when x is -7. So we're forced to stick with x being -7. Like we don't have a choice to manipulate around that part, and we're trying to see what c is at that point. Okay? You guys are right, or if you're thinking plug the hole. But we have to do this with limits, so the limit from the left, limit from the right kind of idea, okay? So limit from the right, that's -7, is c. So that's not a big deal. Over here, you use that. Is anybody going to ask about 9, or can I use that space?
That
We
wasn't
didn't
on
do
our
that.
homework.
Oh yeah, we didn't. Thank you.
Well said, Jones.
Thank you, Trevor.
Gonna go ahead and factor this. So we're using that strategy of algebraic manipulation. I'm gonna move this actually. And just write. So from the right, notice that in this case, x not equal to 7 kind of accounts for both sides. Anyway, as we get into the simplifying, and then we can plug in x minus 7. We can plug in -7, I mean. Equals c. What would you do to solve that? We're safe to solve now. Everybody, I probably should change color, but notice I plugged in the -7x value there.
Yeah, multiplied by c.
Multiply both sides by c.
So c squared.
Okay, so what is that? Where is the issue there?
Can't square, or you can't root it.
Yeah, we're like we can't square root a negative without complex. So can we make this? Sorry, I saw that little mark and was hoping I didn't miss something. Can we make this one continuous?
No.
Okay.
Does that qualify as an answer?
No.
If it doesn't, if you can't fix the problem, then yeah.
Just make
Yeah.
So it just does not exist or not continuous.
Yeah. Not continuous at -7 or unable. Who asked about this one? Did that help?
Mm-hmm.
The notation thing I was talking about just a second ago is really we need to be showing that we're dealing with limits when we're doing this, not just plugging in numbers to the function, because this process of simplifying, like really what we're doing is thinking about simplifying a limit and then plugging in the 7 because we're taking a limit. In other words, this red step right here came because of this notation of limits, not like we're just plugging it in.
That's kind of what I was asking. So like for this type of situation where it can't equals a number you need to plug in, you just take like one side that equals C and then the other separated into a negative and positive, so it's not like technically equaling that number. Is that what I'm getting at?
Yeah, because we're dealing with this case.
So you take
We're
one
trying to figure
side.
out, like, let's say our point is up here. We're trying to move that point in to plug it.
Yeah.
And the only way to know that value is to know what the limit is coming in from either side.
So
Because
let's-
otherwise, you don't know that value. Like, if you plug the x value for that point in, you're going to get does not exist. Or undefined denominator, like this one.
Okay.
Right? Like if I plug -7 here, it doesn't solve for the y value. So the y value comes from the limit. We kind of had a workaround in the prior courses where you just kind of ignored the parts that you canceled off and solved for the y coordinate there. But this is the idea behind it, which is limiting value as you get to that point. You guys remember doing that at all? It's been a while. Okay. Other questions?
12.
Same page?
Yeah.
Same section, I mean? Alright, so same idea, same concept. So we're trying to find the limit, and we're going to 0. And then our other one is b. Because the other side is just b, essentially we're trying to find the limit of this guy, right? Have you kind of picked up on that pattern? So we go back to 1-6, I think it was, where we manipulated our limits. Hi.
Hi.
This is 2 days in a row.
I know, same person.
Same dude.
Thank
Dude,
you.
you're causing trouble, Trevor. Thank you. So as soon as I see the sign is not part of a function like a cotangent, cosecant, secant. Like it's not one of these kind that we need to rewrite with the denominator. So as soon as I see sign, I'm thinking to try to get it into this form. Do you remember what the value was? 1. Okay. Work on memorizing that if you haven't, because remember there's no notes on AP. It's just whatever's in your brain. I will eventually give you, unless you want it now, you guys can tell me. I will give you things. It's a packet of things you just got to know, and it's a lot. So let me know when you kind of want that. A lot of it won't make sense yet at all, but this should be on there, or should be in here. So can we make this look like this? That's really the question. And by the way, this is the same as the warm-up idea, okay? Well, we know that we don't want the 5 involved with the sign, right? So pull it out front. And you can write it as limit as x approaches 5. I'm also going to pull the 4 out front because it's not going to help me match with the 3x. So pull it out front also. And I'm just using algebraic properties of limits to separate these. So now I have sine 3x over x. Well, that's pretty close to looking like,
By 3 at the
yeah.
bottom.
So what if we just multiply this by 3 over 3. You have to do it by the same in the top and bottom, otherwise you're changing its values. Which of those 3's get pulled out? I think you said pull out, right?
Like hold it, just like withhold it, like it stays there, the top one. If you get what I'm saying.
Yeah, I think. So I'm going to change this whole thing to equals now because we're ready to evaluate. At least I think we are. Hold this 3 up here with these guys because it's not doing anything. And then this whole business, actually let me include that denominator. That just becomes 1, right? So now we just get 15/4. Now I didn't show the setting equal to b because we're I guess I could here, but we know that is b. That's what it would take to plug that. Does that help?
Yeah.
Did some of you get that? Good job. Did you get stuck? Okay. Devin, will you show him how to do it? Okay. Any others? Are we good now?
I want you to tell him to not take me.
Okay.
Say you're off limits.
I would like to tell him that. Let's talk about this warm-up problem now. Maybe it will, now that we just did that sine one, maybe you'll see how this one works. What is cotangent?
Inverse sine over sine.
It's cosine over sine, right? What did you say?
Cosine over sine.
Oh, yeah, good. So, here's something interesting. This one would be a good one to make note of and maybe like mark in your book or wherever you're writing it. So we're going to, again, set it equal to k, but in order to do all the substitution, we are heading towards 2 here. And what can we do to this to make it look like, darn it, we cannot talk and write at the same time. Hold on. There we go. And that's k. How can we kind of manipulate this around to look like the one we just looked at? Well, at least a version of it. Let's say it that way.
We separate the limits.
Okay, we could separate and also factor that guy. I'm going to switch this over here, this x minus 2 for now, and just write the cosine of x minus 2. Why did I do that?
It's still the same equation, and then you can get sine of x over x somehow, is what I'm seeing.
Well, it's a version of it, yep. Do you see
It's
Oh.
still the
that
same.
guy?
It's equal to 1.
Even though it's x minus 2, it's kind of that same version, right? Okay.
It's still essentially the same.
Wait, is this one equal to -1 because it's on the bottom? Or is it
No,
still
it's the same.
Still 1?
Yeah. He just asked me this, like, is this the same? Is it still 1? And the answer is yes. However, no, never mind. Okay, so that, and then what do we do with this 3?
It just
Get rid of it.
No, we don't get rid of it.
Oh,
Doesn't it just come over here with this?
Yeah.
I was gonna say so.
Okay. So 3 cosine x minus 2. So x is 2, so that makes this 0. What's cosine of 0? 1.
Oh.
So 1 times 3. Okay? It's good news, I think, that we have 14, 15, 16 left of limits, and then we kind of get away from them. Not that we'll never go again, but In fact, we define in the next unit, define derivatives using, which is a huge concept in calculus. We define those using limits, but then we start using them, and you'll be very happy about that. All right. Go to 14 then. Oh, it's good. Is it good?
This one?
Yeah.
I guess so, yeah.
What is it?
It's a pumpkin pie.
Yeah. All right.
It might have to be your one out of your one Starbucks order of the year.
I wouldn't be able to get it.
Why?
Well, I have celiac disease, so I don't eat out. I have to be super careful. So when I do my one Starbucks a year, it's a decaf Americano with milk and sugar.
That'd be
Yeah, I can't even do their syrup, I don't think. So it looks good. Look what we're starting to see. Infinite in there.
Whoa.
So the next two sections are going to involve infinity, and the next one will be better. This one's a little bit familiar in terms of infinite limits and limits as x goes to infinity. So this will be the next section, but it's cool. I think you'll like that. This one I think will be pretty familiar. All right. So just a quick kind of prep question. Which of these has a vertical asymptote at x equals 3?
H of x. Oh wait. F of x. F of x.
So vertical asymptote at x equals 3. Chloe, you good? The weekend's almost there.
3 days.
That's nice.
Except for.
How about this one? Yes or no? This one?
No.
Why not?
Because they can.
So it has a hole. Same. How about this one?
Yes.
Yeah, because it's x minus 3, x minus 3.
Yeah, me too. The only
Which, tell me about what that would look like if we supposedly have a hole and a vertical asymptote. Do you actually have both?
No, it's just a vertical.
Like which one sort of takes priority or
Vertical
is the boss? Yeah, like if we have an asymptote that the graph is avoiding, we're not going to have a hole there, right?
Take that hole.
Wait, why is it right?
Because it does have this other factor of x minus 3.
But wouldn't that be x plus 3 because x minus 3 factor?
Is there?
No, because this one is x minus 3 quantity squared, so that means there's 2 of them.
Oh, okay.
Yeah. Alright, so you kind of know about vertical asymptotes. Here's some various versions of what we call infinite or non-removable. They're kind of faint, but can you see them good enough to get the idea? Just a reminder?
Yeah.
Okay. So, by the way, one of our jobs is going to be to use calculus to decide is it doing opposite as it comes into our asymptote or the same, like that. How do you think you could use what we know so far to determine that? Because like in algebra and pre-calc, you just have to graph this. You know, if I gave you a function, you didn't necessarily know which one of these it was. So we did a bunch of point checking, which was super annoying. Right? Like check closer and closer to your asymptote, see what it's doing. If as soon as I say closer and closer in calculus, what am I talking about? A limit, right? So how do we distinguish between these two, do you think? Using limits.
The limit is probably the same with the first one where it's different. Oh wait, never mind. Wait, hold on.
Since we know it's a vertical asymptote, we know the limit won't exist.
Yeah.
So if we want to know, does it dive from the left and soar from the right? How do we determine that using limits, do you think? What's the idea of limit? Yeah. Yeah.
Where the function approaches.
As it gets how close?
Infinite.
Yeah, like super close, right? Infinitesimally different. So let's say this vertical line here is x equals 3. If I want to know if this function dives or perhaps soars from the left, what values could you check?
You get its value from the negative and the positive side.
Okay, so what values would you check? Would you check?
2.99.
2 point or not. And then how about on this side?
3.00.
Yeah, like super close on the other side. And that's really the idea here. Okay? Okay, so we're going to use this language somewhat to describe this. So if we're coming in and it's soaring up, it's growing without bound, meaning it will never stop. Okay? Definitely these are non-removable, and the left and right limits at a specific value of x have to be growing without bound in the same direction for us to make that claim. Here's what this is going to look like. Let's get to that packet. We'll come back to these. Am I hitting the right button? There we go. So what do we need to do to find vertical asymptotes first, typically? It's factor. So let's factor this guy. So what do we know? Yeah, there is. Where's our vertical asymptote? At x equals 3. Okay, so we know there's actually happened to be the number I made up. I'm not sure why that worked out, but on the picture. So now we know there's a vertical asymptote there. But we want to know, is it going to be this kind there? Right? Or is it going to be this kind? I know I'm sketching a lot, but you get what I'm asking?
Yeah.
Or any other version that's, maybe they're both going down. So what is the limit as x approaches 3 from the left? Well, it says evaluate it. So the limit as x approaches 3 from the left requires us to plug in what? Okay? And we don't have to use these because they're not really contributing to the behavior everywhere else, just at the point. So let's say 2.999. And something like that. Okay, well what's going to be true on the top?
It's gonna be
Nearly what?
pretty much one,
Yeah, pretty much 1. On the bottom,
but not this. Or it's gonna be less.
okay, so 2 things about the bottom.
It's hard to hold.
This will be two things. 1, it will be negative, which turns the whole thing negative. Is that what you said? And then talk to me about size also.
Size.
Yeah.
It's really small.
It's going to be really teeny, right? That we chose that point and it's barely away from 3. So in this case, it's going to be a really tiny number. So what does that do when you divide by tiny?
Big number. Good call.
Like if I say how many pieces are in a pizza, you would say 8. If I said how many molecules are in a pizza, you would say billions, right? Like divide by tiny makes things huge. So we're combining these two. We're saying negative and dividing by tiny means what will be true for the overall.
That's very.
I need to hear it.
Infinitely
If
negative.
it's negative, and we're dividing by something super small, which makes a very large number. So negative infinity. Do you hear kind of that combination in there? Okay. Maybe we'll write that. If we divide, let's use the symbol. We divide by tiny, not Timmy. It makes huge. Okay? Negative huge is what? Okay, so one thing you're going to need to think about as we get into infinite. How do we make things huge, or either really big positive or really big negative? Or what happens if we divide by really big positive or negative? In this case, how do we make it that way? Okay, so if we're dividing by a really big negative, that makes it 0. If we're dividing by a really tiny negative, that makes it negative infinity, and vice versa. Okay? So what is this coming into 3 from the left? What does it look like? It's diving. It's going really big negative. Okay? So it's diving down to the left. Okay, and then from the right, what are we going to pick to use? Yeah, like let's do a couple zeros there. I don't, I'm kind of writing it with it filled in, but just using the idea of it. What is the numerator going to be? Close to 1, and now it's positive again. So I should have done this over here, but the numerator is positive. Positive, and then tell me about down here. It's positive small, so we're still dividing by tiny, because we could have added a whole bunch more zeros, right? Remember we said infinitely close. So down here, no, not yellow. Down here we want positive, positive, tiny. When we divide by positive tiny, we get positive infinity. So, do you see it doing this in your mind? Yeah. So to me, this is so much better than the algebraic way. I don't know if it is for you, but it is for me. Does it make sense though? Sometimes it takes a little bit to wrap your head around how to work with infinity. It just is not something we do very often. But calculus is all about infinite and infinitesimal in a lot of ways. All right, next one. It says limit as x approaches 3 from the right. So what are we looking at? See if you can do this without plugging numbers in and writing them. We're asking, is this going to positive or negative infinity? Because we know there's an asymptote, right? At 3. That's why we're checking 3. So is this positive positive infinity or negative infinity? From the right. Yeah. So what's a good number? If you just think about it instead of write it, what is a good one to plug in from the right? Like just over 3, right? So the top is going to be negative, and what's the bottom going to be? Positive and tiny. So negative over positive tiny is? Negative infinity. Okay. Alright, next one. It's telling us to check for 1. I could see them giving you one where you have to decide where to check. But we're checking at 1. So this notice also doesn't say left or right. So let's split it. So from the left, is it going to do us any good to factor, by the way?
No.
No.
It's not going to cancel anything, but I kind of think it might be easier to see. What do you guys think? Right? So this would be x minus 3, and then how does this bottom factor? So I guess you could do x minus 1 squared if that is easier, but it's easier to plug in your brain to plug in stuff there than it is into this squared function, especially because we're dealing with small little decimal values. Okay, so from the left, what will these two do? Like, what's a number that will come in from the left of 1? Yeah, like 0.99999, right? So what will both of these be? So I'm just going to write it like sign symbolically. So it will be negative and tiny, right? I think it's still helpful to write that word. What happens when you multiply tiny by tiny?
Even tiny.
Even tinier. So we're just kind of talking number sense here. So negative times negative, and then in the denominator we're doing, or in the numerator, excuse me, 0.99 minus 3. What's it going to be?
Negative.
It's negative, okay? And it's not tiny, so who cares about that? So negative divided by positive,
Equals negative.
negative infinity. How's this working for you? Do you like being able to just conceptually think through it rather than actually plug in? It's nice, right? I like infinite limits myself a lot. I think it's cool. You'll see next section why even more, I think. Alright, now we're coming in from just above 1, which is still going to be negative on top. It's still going to be tiny times tiny on bottom, because it's just barely bigger than 1. But now it's going to be positive on both of these. So did that change our final result?
No.
No, this is still going to be negative infinity. Okay? So if we sketched it, we know there's some kind of asymptote at 1, but this time it's going to come in and dive both of them. Does this kind of make sense?
Yes.
It's a little less work. Yeah.
So then for our answer, since it's final limit, we just say limit as x plus 1 equals negative 1.
Yeah, and we have to be careful because it's technically not a finite number, right? It's negative infinity. They do agree, like they're coming in from both sides. It's both, in this case, negative infinity. So that allows us to be a little bit more flexible. Here's what he's asking. Limit as x approaches 1. Is it okay to say that since it's the same? We would say it grows without bound in the negative direction. It's not technically a limit. It's not a limiting value because infinity is not a limit, right?
Yeah. So it goes without bound in the negative direction. So we say from both sides.
No, just you don't have to. Well, I mean, it's not wrong to, but you could say this: f of x grows without bound. Are you guys good with abbreviation without bound in the negative direction? We do have to say that it approaches 1 as x approaches 1. You don't have to say from both sides because we're combining that to say just as x approaches 1. And the assumption would be if it was different, we wouldn't write this.
Yeah.
Yeah. Or we would be more specific, like this one. Right? Okay. Any questions on this? So we're, like I said, getting close to the end of the unit. We have horizontal asymptotes, which is as x goes to infinity. If you notice, all of these, we're still taking x to a real number. The next section, we'll put infinities in here, either positive or negative. And it kind of does some cool stuff to the math. And then the last one is a theorem. So section 16 is a theorem that we're going to learn called the intermediate value theorem. And that starts pushing us into FRQ territory where we have to justify stuff. So there's some specific things you have to say. And then we're done. So I have a review on AP Classroom. It's called a progress check. And there are 3 multiple choice ones and entire assignment and 2 FRQs. I've only assigned you the first one for now. It's to start reviewing, okay? And it goes back to the early stuff that we did 2 weeks ago or so. So take a look at that. Should be going live here in just a minute if it's not already. And it's due Tuesday. I think it's due Tuesday before class. I'll double check. Okay.
Did you hear that, Devin?
If it feels a little weird and uncomfortable, go back to those early notes. Some of it is on like rates of change. Remember average rate of change versus instantaneous even? Remember that stuff? The concept of secant versus tangent line. So it goes back to some applied uses of that. What else? I think that's all. Well, you should probably do a couple of these. Let's see if we can make this painless. If you're good with not finding the vertical asymptotes and just doing this part, like evaluating the limits so you know if it goes to infinity or negative, let's just do like 14 through the end. So 14 to 18.
So this for me, when he says 14.
How are you guys doing with the workload? Does it seem reasonable? I feel like it seems like when I'm asking and talking to you that you're doing well with your understanding.